Welcome to today's introductory session on the subject Automata Theory and Computability. The subject code 18CS54. In this subject, we are 5 modules are there. Before going to the details about the modules, let me tell you about the textbook which you need to refer for this particular subject. The textbook name Elandridge Automata, Computability and Complexity, first edition, Pearson Education, whether it is published in 2012 or 13, no issues. Then the other textbooks which are mentioned in the syllabus, you can refer them. Apart from these also, you can refer any other materials which are available, genuine materials, you can refer them. So now coming to the modules or what and all we are going to cover in this subject. So in the module or the introductory modules, we are going to cover what is the importance of this subject, what are the basic elements to study this subject, and the other concepts like finite state machines and the variants of the finite state machines we are going to study. In module 2, we are going to study the details about how the regular expressions are formed. And in module 3, we are going to study about the details about the grammars, what type of grammars are available, how to write the grammars, all those things. And in the module 4, we are going to study about the Turing machines problems, how to write the Turing machines or how to design the Turing machines. And then the last module is a little bit theoretic, which covers about the algorithm decidability, the languages related to that, and little bit about the NP complete and NP hardness problem and the quantum computation problems. Okay, this is a little bit a brief discussion about what and all will be covered in all the 5 modules. Coming to the first module, we are going to talk about the introduction or the basic elements of automata theory, what and all is required. So before exactly going to that, okay, so we are going to study where exactly, what is the definition of this automata theory and where exactly the concept of automata theory is practically used, or in other words, in practical applications, how exactly this concept can be used. Okay, so before going to applications, let me tell you what is the definition of this automata theory. So automata theory is the study of abstract machines and the automata. So if you want to design a system, whether it is existing or whether it is proposed, so if you want to build a machine for that system, or if you want to design the system, so you can take the help of this particular subject. Okay, and all the computational problems can be solved using them. Now coming to the applications of finite automata, we all may wonder that where exactly this particular subject can be used in practicals. So the first and foremost application, or one of the major application of this particular concepts or this particular subject, is during the designing of the compiler. So when you are designing a compiler, so as we all know, compiler will be converting the high level language which is being written by the user to the machine language or to the low level language. So in the entire process of conversion, you are going to deal with many phases. So the first and foremost phase of the compiler is the lexical analysis phase. So basically the lexical analysis phase is used to divide or to break the entire statement what you have written as a part of the code into different tokens. Okay, for example, if you are taking a statement like if a greater than 10, then if assume that this is your one line of the program, part of the code or part of the line if will be considered as one particular token. Then your brackets, your identifiers, your symbols, all those things will be considered as one token. So identifying the tokens, okay, is a first phase of the compiler. So in that phase, to identify the tokens of your statements, the lexical analysis phase is used. So to design that lexical analysis phase, you can make use or you can take the help of this finite automata concepts. How exactly this is being done? So that we will see in the coming concepts, but in the lexical analysis phase of the design of the compiler, we are going to majorly use the concept of finite automata. Then the other usage or application of these concepts are in recognizing the pattern using the regular expression. For example, if we want to recognize a pattern somewhere, okay, either it might be in the web page or it might be in the document, you need to match the pattern. So how to match that pattern? For that also we are going to make use of the concepts of finite automata. And then if you are designing a digital circuit, if you are designing a text editor and in spell checker, or if you are scanning a web page, so in all major applications of our day-to-day life activities, you can make use of the concepts of this finite automata. Okay, so these are the applications of the finite automata what we studied. So now before going to the exact concepts of automata theory, so let us understand the basic elements which are used in the automata. So the first element is the alphabet. Okay, so what is that alphabet? That we will study later. The next element which you are going to, which is very important, is the strings. Then what do you mean by empty string? Then the length of the string. Then what do you mean by the alphabet or power of alphabet, and how to concatenate the strings, and what are the different operations we can do with the strings, and then the languages. So these are the major components, or you can say elements, which is used often in the studying of the concepts of automata theory. Yeah, so the first element which is used in automata theory is the alphabet. Okay, alphabet usually is defined by the symbol sigma. Okay, all the symbols which you are going to use in your entire operations of automata is called as the alphabet. Like for example, usually you can define the alphabet as a set of elements, set of non-empty elements. Okay, is called as the alphabet. Okay, and these non-empty elements can be a comma b, 0 comma 1, or anything like that. And strings is another element of the automata theory concept, and strings are formed from the alphabet which is defined in the set. For example, in the set which I have defined, the alphabet is being given as a comma b. So using those elements of the alphabet or elements of the set, we can form the strings. So the string, one of the string which is formed from the alphabet set is A, AB, ABBA, BABA. So any string I can form. So string, in the string, the symbols which are available in the alphabet set can be repeated. Okay, because string is not a set. Okay, remember, string is not a set. Okay, string is formed from the elements of the set alphabet or alphabet set. Okay, then let us understand what are the operations which you can perform on the string. So now, for example, if you have defined a string, okay, as W, which is A1 up to AN, N can be any value, and V is another string which is B1, B2 up to BM. So you can form the string with W as ABBA and BBAAA or any value you want. So now if you want to concatenate a string, okay, so you can, these two strings, so WV, you can append the first string, that is W, and then you can append the second string B 1 up to Bn. So in this way many operations can be performed on the string. So if you want to reverse a string, so if W is your string which is ranging from A1 to AN, then WR will be AN up to A1. And finding the length of the string, so if you want to find the length of the string, so find the value or find how many elements are there in the string. So in this particular string the number of elements are 4, so the length of the string is 4. Okay, so the length of the concatenated string you can find out like this. So if the string is not having any letters, okay, can be represented by lambda, okay, and the length of the string can be mentioned as 0. And if you want to find out the substring from the given string, so that also you can do. And you can find out the prefix and you can find out the suffix. All the operations what you are going to do in the normal string, so the same thing can be done. So now if you want to find out the power of the string, so you can find out by using these operations. Okay, so now the important operation which is commonly used in our automata theory concept is the clean closure concept. Okay, so that is sigma star. Okay, so sigma star is defined as the set of all possible strings, okay, from the given alphabet. Okay, so this set usually will be an infinite set because we don't know how many strings will be formed from the given alphabet. So that's why sigma star from the given set of alphabet set will be usually infinite. So it can be sigma star, it can be consisting of the empty string also. It can consisting of only one alphabet also. It can consist of only the letter B. It can consist of only two A's, A, B, like that. So all the strings or all the possible strings which can be formed from the given alphabet set symbols is called as a sigma star. So remember that sigma star will be containing the empty string also. Okay. Then apart from sigma star, so you have another operation which can be performed on this is sigma plus. Okay. So the difference between the sigma star and sigma plus is sigma star will be consisting of all possible string from the given alphabet which consists of the empty string also. But in case of the sigma plus, the sigma plus contains all possible string from the given alphabet set, but it does not contain the empty string. So in other way, the sigma plus can be defined as sigma star minus lambda, which without the empty string. So if you can understand the difference between sigma plus and sigma star, sigma plus is mentioned as AB, AA with all possible string from the alphabet AB, and sigma star is containing the empty string. So it is important to know the difference between sigma star and sigma plus. Okay, then the concept of languages will come into the existence. Okay, so a language is any subset of the sigma star. Okay, so for example, if your alphabet set consists of AB, so your sigma star will be empty string, then all the possible string which can be constructed from the alphabets set AB. So the languages you can define from this alphabet and from the sigma star are lambda you can consider as one language, or empty string you can consider as one language. Then all substrings or all subset which can be formed from the sigma star can be considered as a languages. So languages play a very important role in our entire concept of automata theory. Okay, the normal operations of sets, fine. And in the languages you have two different languages. So the first language is the finite language and the second language is the infinite language. Okay, so an infinite language means a language where you cannot restrict on the strings which will be coming under that particular set. For example, if I write the language L as A per n, B per n, where n is greater than or equal to 0, okay, then the strings which are coming under this particular language I can write as lambda, that is empty string can also be a part of this language. Then the other string will be AB, the other string will be AABB, then the next string can be AAA, BBB, okay, etc. Okay, I cannot have a restriction. So this is an example of infinite language. But if I write the string as ABB, okay, then this string will not be belonging to this particular language. The reason is the language is being given as what? A per n, B per n, where after number of A's only the same number of B should come. So only those strings will be a part of this particular language. So the language, the string ABB will not be belonging to this particular language. So in that way you can find out whether the string is belonging to the language or not. Then you have this is the example for the infinite language. And apart from this, you have some finite languages also, where you can tell, you can restrict the number of strings which are coming under that particular language. For example, if I say the language as A power 3, B power 3, okay, where n greater than or equal to 0. So I can say all this particular language is a finite language, where the strings like the L contains the strings like empty, AB, then AABB, then AABB. So in this way I can write the restrict, or I can restrict on the number of strings which are coming under this particular language. So in languages, as I said, you can write the finite languages also and you can write the infinite languages, where the infinite language will not be having any restriction on how many strings will be coming under that particular set. So this is about the basic elements which will be coming under the entire concept of automata theory. The next session will be continued with the concepts of finite automata, how you are going to design the finite automata, whether it is deterministic or whether it is non-deterministic, how to convert that, all those concepts you are going to study in the next class. Thank you.